vector space means the sum of two homomorphisms will be a homomorphism, and we have defined already how is this the operations. So here are for say T1, T2 in home VV. We had already defined this T1 plus T2. So this is the map V to V, and by so this is V under T1 plus T2 is same as V under T1 plus V under T2. And also that alpha T is also T1 T2. And this alpha T is also a map here. Alpha T is also a map V. This is defined by, so alpha T operated on V is same as alpha then V T. This is here V. So we had already proved that T1 plus T2 and alpha T are homomorphisms of V into V if T1, T2 are homomorphisms. And with respect to these operations, we had already proved that this is a vector space, and in case the dimension of V over F is M, then the dimension of the vector space home VV over F is M square. This is already proved. Now, when we talk about vector space, then sum is defined of two elements, and a scalar multiple is also defined, but the product is not. However, since these are maps and natural product can be defined by taking the composition of two maps, and therefore we shall also define now. So define now T1, T2 as the map from V to V, and remember that what we shall be discussing now onwards will be that V is a finite dimensional vector space over the field F. So V goes to V under T1, T2, and we define this as VT1 under T2. Now, thing is, what you can see that since T1 is a map V to V, so VT1 is also in V, and T2 is a map V to V, so this makes sense, VT1 under T2. So if you define the map like this, then first of all, this map is well defined, that I leave for you to verify. And also, you can prove that then this T1, T2 is also a homomorphism. Is also a homomorphism of V to V. For this, you have to prove two things, that it preserves sum and it also preserves scalar multiplication. So number one. So if you have two elements, say U and V, in so for U, V in V, and alpha in F. So first of all, this U plus V under T1, T2, the way we have defined, this is here, this is on T1, T2, U plus V. So first T1 will operate here, so U plus V under T1, and then this whole thing will be under T2. Now T1 is a homomorphism, and therefore it preserves sum. So this is same as here U T1 plus V T1. and now this is under T2. Now UT1 and this VT1 both are elements of V, and T2 is a homomorphism, and therefore here UT1 under T2 plus VT1 under T2. And the way we have defined T1, T2, so this is U under T1, T2 plus V under T1, T2. So it preserves this sum, you can see here. And the second thing that we want to see is what about the alpha V. So alpha V is an element in V, so we want to see what about alpha V under T1, T2. Now this is defined as alpha V under T1 and then this element under T2. Now T1 is homomorphism, therefore this is same as V T1 and this under T2. Now VT1 is a vector, you can call it say U, so this is T2 of alpha U. T2 is homomorphism and therefore this has to be alpha then U T2. U T2 is what? V T1 under T2. This is what it is. Now the way we have defined this is same as alpha, and this is V under T1, T2. So you can see that alpha can be pulled out. So it proves therefore that T1, T2 is also a homomorphism. There are other properties you can see that hold true for this. The other properties can be verified. So, for example, you can check the distributive law. So, T1 plus T2 and T3 same as T1, T3 plus T2, T3. That is from the right, and from the left also T2 plus T3 same as T1, T2 plus T1, T3. The distributive laws. Right distributive law and the left distributive law. This composition or this product is actually associative also. So this property means you can verify that this T1, T2, T3 is same as T1, T2, T3 associativity. You can also see this that alpha T1, T2. Now, once T1, T2 are homomorphism, as we have proved, T1, T2 is also homomorphism, and this home VV is a vector space. Therefore, alpha you can call T1, T2 as T. So alpha T is also a homomorphism. Likewise, this alpha T1 and T2. This is composition of these two homomorphisms. Like that, also this T1 alpha T2. So these are three homomorphisms in this way. But you can prove that all these three are equal. So this is true for all T1, T2, T3. PV and for every alpha in F. Well, recall if you can, there is one more thing also one can see is that the identity map. The identity map from V to V, which is defined by V going to V under I as V only. So this is the map here. Then this I is also a homomorph. And is also can be seen that I and T, they commute. I and T commute for every T. And in fact, can also prove that this alpha T commutes with, alpha I commutes. So this is alpha I and T. T alpha I. Yeah. So in fact, the map alpha I. So alpha I would be the map that will be V to V. And that will take V to this under alpha I. That means what? This is same as alpha V under I. That means this is alpha V. So for every scalar alpha. And this can be seen that this commutes with every T there. So this is the center. Now this I is the identity map and it serves as this. So now recall a ring. What is a ring? So recall what is called a ring. So a non-empty set R together with two binary operations. So this is called a ring if number one with respect to addition, this is an additive abelian. Is an abelian group. And with respect to multiplication, this is closed. So R is closed with respect to multiplication. That is, if R and S are two elements here in R, then R, S, SR, both they are here in R, naturally. And third thing is that the multiplication distributes over addition. That means both the laws from the right as well as from the left. So that means R plus S T is same as RT plus ST, and R S plus T is same as RS plus RT for all R, S, and T in R. I have written R like this and sometimes like that. Now you can also write this the same way. But if you are reading Hurston, for example, then he includes associativity in the definition itself. And if you are reading Jacobson, for example, in that case, he does not include associativity of multiplication in the definition of the ring. If the ring has some more properties that is with respect to multiplication, accordingly, an adjective is added. So, for example, if it has identity, then this is called ring with identity. Associative ring. However, associativity in definition itself is included. by Austin, but not by all authors. Likewise, if the product is commutative, then it is said that R is commutative. And one more thing, that if there is an inverse, then you can call that the element R inverse is S if Rs and S are both are equal and equal to the identity of the ring. By inverse, we shall mean from both sides, not just one side. So accordingly, the ring is then called. All right, there is. So you can see now, as far as this home V is concerned, if we allow this product also, in that case, this becomes a ring. It's a vector space over F, and it becomes a ring also. And this ring has identity, namely the identity homomorphism, and it is associative. So this is an associative ring with identity. So we also can see there is something more, which, as I said, that this alpha I commutes, but there is something more here also is there. So we define what is called an algebra over F. So home, home this B is a vector space over F. It is also an associative ring with identity. Whenever we put these adjectives, that is with respect to multiplication, because with respect to addition, all 5 properties that could be possible are already there. Okay. This is the map identity homomorphism. But it has something even more interesting properties. We define what is called algebra. So let us say what is called algebra. Now, an associative ring A is called an algebra over F. It is a vector space. That means it's a ring as well as vector space. And one more property. So, an associative ring say A is called an algebra over a field F. If A is a vector space over F, and has the property that for AB in A and for every alpha in F. Now, see, since this is a vector space, therefore alpha A, alpha B, they are elements. So alpha A, alpha B, they are elements of A as well as alpha B. Now, since this is a ring, therefore AB is also an element here in A. And so is, because it's a vector space, therefore scalar times this also is an element. Now alpha A is an element of A, it is a ring, therefore this product is also there. Alpha B is an element of A, and A is a vector. A is an algebra, therefore the product algebra is a ring. So A times this also is an element of A. Now what this property requires that all the three should be equal. So what is an algebra over F? It's a vector space over F. It is an associative ring, and in addition to that, it has one more property that relates the scalar multiplication to the multiplication of two elements in A. Good. Now, what is interesting here, once we have made this as an algebra, we shall not be calling this as a home VV. So now this, since home VV over F, we had already seen this is a vector space over F, this is a ring over F, and this is the property that alpha T1 T2 is alpha T1 T2 is T1 alpha T2, and therefore this is an algebra over F. To distinguish that we are allowing composition or the product of two elements here, that means we are treating this as an algebra, not just vector space. We give it a different name, different notation. So we shall be denoting this algebra will be denoted by algebra over F, which is obtained from this vector space. And the elements will not be just called homomorphisms. To make this clear, that combination, the composition of two maps are allowed, these elements will be called the linear transformation of this will be called linear transformations. Good. So henceforth, when we write AFV, that means set-wise it is same as home VV, but this is now treated as a ring also, as an algebra. So the composition of two homomorphisms, which is now the product of two linear transformations, is also considered. Now, what is a very important theorem in group theory that we have already done is that every group is isomorphic onto a subalgebra of group of all homomorphisms of G to G, that is automorphisms. A similar sort of result is also here available. So an analogous to this Calais theorem is now here for the algebra. So this lemma or theorem, whatever you want, you can prove before that. So if A is an algebra over F and is with identity, so if A over F, so call it say A only, is an algebra over the field F, with identity. So it has identity. Then it is isomorphic onto a subalgebra of, then it is isomorphic onto a subalgebra of AFV. What is AFV? AFV is the algebra of all linear transformations of the 2V. So we prove this. So to prove this, what we need is for some vector space, or some vector space V over. So to prove this, we need some vector space. So we start with what is available already with us, one vector space, namely A itself. So let us take V to be A itself. So let V to be A itself. Then V over F is a vector space. Over F. Now what we need is we need a map that should be from. So we need to obtain a map, say psi, from A to AF. A going to psi, which should be a homomorphism, algebra homomorphism. Homomorphism means, so here a homomorphism is a vector space, that means it preserves sum as well as the scalar multiplication, and as a ring also. So it should also preserve the product, which should be an algebra isomorphism. So it should preserve sum, it should preserve scalar multiplication, it should also preserve multiplication. Now, and it should also be one-to-one. So such a map is needed. Now, ASI is basically has to be an element of AFV. AFV consists of linear transformations. They are mappings from V to V. So these mappings, ASI for every A, ASI should be defined. So now take, for example, define say TA. Here for every A, V to say V. So define for every A in A, TA, that V goes to V under TA. Define this map as VA. Now this VA makes sense because V is A itself. So V is A itself. And A is an algebra in which the product is well defined. So VA is an element of A. So VA is an element of V. So define this map TA. Now you can prove that TA is a homomorph. Now TA is a homomorphism. You can see here. So TA is a homomorphism means we need to prove that it should preserve. This is V2. V2V. So this has to be an element of AFV. Now this TA is here in AFV. That's what, and we shall take A psi to be T. So for this here, what we need to prove that this is a homomorphism of V into V. So it should preserve sum and it should also preserve the product. So for UV here in V and alpha in F, number 1. U plus V of TA, how we have defined? Multiplied on the right. Now U and V, they are elements here in A, and this distributivity is there in the algebra. So this becomes UA plus VA, and this is U under TA plus V under T. So TA preserves the sum, and the second thing is that alpha V under TA. How we have defined? A multiplied on the right. Alpha V A. Alpha V A. Now this alpha VA, VA is V under T. So you see that TA is a homomorph. This is here an element here in AFB. So set wise the two are same. So the next thing is that A psi, if we take QBTA, will it serve our purpose? So what we are having is that let us take this A psi TA for every A in A. So let me recall. So what we have is the map now psi, which is A and V, same. And we take this to V to V. So this V goes to, this A. A goes to A psi. A going to A psi. Define this as TA. So this TA is the map V to V. How is it defined? V going to V. So V under TA is V. Now that's how the picture is. Now this psi, we say that this will do our job. So what we claim is, therefore, psi is an algebra homomorphism here. So this is V to AFV. So A to AFV. So this is A, F, an algebra isomorphism. That means it's algebra homomorphism and is 1-to-1. So for this, what we see here is that the psi is homomorphism. First of all, as you can see, number one. So it should be as a vector space homomorphism and as a ring also a homomorphism. So as a vector space, it has to be a homomorphism, means it should preserve sum as well as the scalar multiplication. So that means that is so it preserves sum means a plus b psi is a psi plus b psi. Second thing is that alpha here psi. Here is alpha a psi. Third thing, so as a vector space and as a ring, therefore AB of psi is same as A psi, B psi, and psi is a one-to-one map also. So this is for all A, B in A, and for all alpha in. So this A plus B psi is same as A psi B psi. Proving this means that T of A plus B equivalently is same as TA plus TB. This is equivalent here because this you can see that A psi is TA. So this is alpha TA, and this is here T. This is alpha TA. This is T alpha A. T alpha. And this last one is that TAB same as TA TB. So this is what we need to establish to prove that it preserves sum, it preserves this is alpha A, sorry. Okay, so number one, A plus B psi is A psi plus no. So what you want to prove is for the sum that TA plus B is TA plus TB. For this, you can observe for every V in V, so T of A plus B is defined as V multiplied on the right by A plus B. All the three elements, V as well as A and B, are elements of A where distributivity is there. So this is VA plus VB. Since V, A, B, they belong to A, and multiplication distributes over addition in A. So what is the case? So this, when you have VA plus this, by definition, that this is V under TA plus V under TB. So this is the first thing that we have seen. The second thing that we wanted to prove, that T of this alpha A is same as alpha A. The T of alpha A is same as alpha TA. So once again, for every V, in V under T alpha A, this is V alpha A multiplied by alpha A on the right. Now recall that A is an algebra and V and A, they are elements in. So this is, recall this, that alpha AB same as alpha A B is same as A alpha B. In A, it's an algebra which is same as V. So this is same as, so this alpha comes out here. So this is same as alpha VA. This is same as alpha TA VN. So that makes T alpha A is alpha TA. And third thing is that TAB is TA PB. So once again, for every V in V, VTAB is VAB multiplied by AB on the right. Now, in A, product is associated. Therefore, this is same as VAB. Since VAB belong to A, and in A, multiplication is associated. Now VAB, this is same as, so this is TB of VA. So this is TB multiplied on the right of VA. VA is V under TA. TB. So this is happening for all V in V and for all A, B in A. So what these things together tell me, that TA plus B is TA plus TB, alpha TA is alpha TA, T of alpha A is alpha TA, and TAB is TATB. That means basically that psi is the homomorphism, algebra homomorphism of A into AF. Finally, that this is psi is 1 to 1. So for this, either you prove map-wise or you can construct the kernel. What is the kernel? Kernel of psi is all elements here A in A, such that the image A psi is 0. Now this 0 is the 0 map. This is the same all A in A, such that TA is 0. TA is 0, so all A in A, such that TA is 0. So V of TA as a map is 0. That means VTA is 0 for every V in V. Now V and A are same, and A is an algebra with identity. In particular, For the identity element in A, the identity of A. This VTA equal to 0 will force what? ETA is 0. ETA means EA is 0. That means A is 0. So this set therefore is, hence what we have, the kernel of psi is basically singleton set consisting of 0 only. So that makes that the psi is 1 to 1. So thus we have proved that this is psi is an isomorphism of A into AFV. That is A is isomorphic to a subalgebra here of, so a subalgebra of AFV. So this is the image here of A shell. So this A is isomorphic to here A under psi, which is a subalgebra of AFV. So this is what. So what we have proved is, which is analog of the Calais theorem here, that every algebra with identity is isomorphic onto a subalgebra of AFV. Now for this reason, AFV is called general linear algebra. So AFV therefore is called general linear algebra. All subalgebras are called linear algebra. All subalgebras of AFV are called linear algebras. So what we have proved is that every associative algebra with identity is isomorphic onto a subalgebra of the general linear algebra AFV. Now this AFV is actually very, very important. So the last thing that we call here is about a property here. So recall what is called a polynomial. So a polynomial over, let us say, f, if f is an expression of the form, expression fx of the form. Let us take this is a naught plus a1 x plus an x. Ai is come from. Good. Correspondingly, if you have an element to say A, so if A in A is such that FA, FA means here A naught, and this is A naught. So to make this as an element of A, so A naught E is A1E is A1A square, An A power n. Now this is an element here in A naturally if this is equal to 0. Then A is set to satisfy F. A is set to satisfy the polynomial F. One important observation is here. So this, if A is an algebra, and hence onwards we shall always assume algebra means associative algebra. So if A is an associative unitary algebra means algebra with identity. It has identity. Naturally, identity here means with respect to multiplication. Is of dimension m over a field, let us say X. Because it's an algebra, therefore it has to be a vector space as well. All right. Then A is then an element A in A satisfies a polynomial of degree at most n. Now, a polynomial over f. So, saying polynomial over f means we say that this is the ring of polynomials over f. And it happens for every element A of A satisfies the polynomial over f, and the degree of this polynomial will not exceed m, where m is the dimension. We say that the polynomial fx is of degree n if an is not 0. Others may be 0 or less. The proof for this is pretty simple. So let us take, henceforth we shall also be writing, instead of writing E, the identity of A, we shall be writing 1 to denote the identity of A. So let us take A in A. Then what we see here is E, A square, A cube, and so on and so forth. They all belong to A, where E denotes that E is the identity of A. So all of them are elements of A. So if you continue, let us say up to m plus 1, A m plus 1 power, and or even just take m only. M only. Okay. So these are m plus 1 elements in A are m plus 1 elements in A. Since the dimension is m, therefore they have to be linearly dependent. Since the dimension of A or F is m, these are linearly dependent over F. That means there exist, that is there exist scalars, not all zero, such that so alpha naught b alpha 1 a alpha 1 a square alpha m a per m is 0 for some not all 0, not all zero elements alpha naught, alpha 1, alpha n, f. That means this satisfies, that means this A satisfies the polynomial fx, that is fx alpha naught alpha 1 x alpha m, and its degree naturally will not exceed m. It will be n in case alpha m is not 0. And degree, of course, of fx does not exist. So this is what we have proved, that every element of this such an algebra A will be satisfying a polynomial of degree at most n. So as a corollary from here, you can prove therefore. So if V is a finite dimensional vector space here, so if V is a finite dimensional vector space over F is n, then for every t in AFV, there exists a polynomial non-trivial. Trivial polynomials are constant polynomials. Non-trivial polynomial, say fx, satisfied by t. And of course, of degree n square, at most n square, satisfied by t. So every linear transformation on a finite dimensional vector space of dimension n will satisfy a polynomial of degree at most n square. In fact, degree fx can be and not exceed n. Once we prove that this is called the Cayley-Hamilton. So that would be much sharper result. However, it satisfies a polynomial of degree at most n square, is established now, and the Cayley-Hamilton theorem will be established later on. So we would like to wind up it here. So thank you very much for your kind attention. See you tomorrow. More results on AFB.
Thank you, sir.